thank you very much. I'm sorry, I realize now when I read the title that it doesn't look very appealing. It's a very long, complicated title.
Speak up.
Yeah, but the microphone does work, doesn't it? Yes. Yeah, so this is so in this talk, I mean, I will. This will talk will have something to do with. Yeah, this talk will be largely about arithmetics, but the work of Jean-Michel Bismut will play a big role in this, because as many of you may know, in fact, Jean-Michel's contribution to work on local index theory plays a crucial role in Arakelov theory. So especially the racing analytic torsion, which appears in the arithmetic Riemann-Roch theorem, which was proved by many people, was then generalized by Bismut and Koehler to a relative situation and could then be used to prove a relative form of the arithmetic Riemann-Roch theorem. All this also exists in an equivariant context, so that, I mean, in these big theorems, arithmetic Riemann-Roch theorems, and Arakelov theory, in fact, Jean-Michel's input it's not simply important, it's almost the core input. So anyway, so here we will see this actor, the high analytic torsion, at play in a particular situation, the situation of abelian schemes. Now, before I begin, I would just, on a more personal level, I would like to say that I have always, since the end of my thesis under the direction of Christophe Soulet, I've always found Jean-Michel very supportive, and also, I mean, very available. I mean, in fact, when you think of the amount of work and the number of pages, I mean, that Jean-Michel has produced over the years, I've always found him amazingly available, and he was always there to explain his ideas. In fact, I remember in particular one instance in Berlin 15 years ago, where I was working on, I was attempting to generalize I was trying to give a combinatorial proof of the Riemann-Roch theorem for high K theory. And for that, you need to sort of consider combinatorial generalizations of the racing or torsion, which can be constructed using the high analytic torsion. And in fact, I mean, it is during a conversation with Jean-Michel, he was visiting Berlin at the time for a week, in the evening, I mean, discussing that with him, that finally the correct combinatorial angle emerged. And in fact, I mean, he pointed out how to do it for K1. Then it became rather quickly clear to me how to do it for Kn. And that was at the end of a day we had already given a talk. He was rather tired, and this was not even an analytic matter. And he was very patient, and yeah, I'm very grateful for that. So, yes, now to the matter at hand. So I would just like to start retelling a rather classical story in arithmetics, but maybe in a rather non-standard way, in a way which is where I have a bias which comes from an Arakelov theory. In fact, I mean, for those of you who don't know what Arakelov theory is, this will not tell you what it is, but at some point I will describe some objects and you will get a feel, you know, what this is all about. It's basically about putting hats over algebraic objects. So so here, let us first consider something very classical in arithmetic. So it is units. So remember, a unit, that's an algebraic integer, and whose inverse is also an algebraic integer. So it's so if you consider that it's an element of a number field, so it's in the ring of integers of the number field, and it's a unit in that ring. Oh, sorry, that's it should be an M. And now units, of course, there's a famous theorem by Dirichlet which tells you something about the unit group in the ring of integers of a number field. It gives you a rank formula for that. And, but on the other hand, I mean, there's the question of the explicit construction of units. And this has been a concern of mathematicians for more than a century, I mean, probably 2 centuries. And I mean, here I'm giving an example of the most standard sort of non-trivial unit, that is a unit which is not a root of unity simply, that can be constructed. And this is the cyclotomic unit, and it's built in the following way. It's simply 1 minus a root of unity, but the order of the root of unity has to be a composite number, that is, a number with at least 2 prime factors. And so this is the really prime example of a unit, and which is not a root of unity. And geometrically, in fact, that's the point of view we'll pursue, one should see this as being built from the torsion points of the torus, which in fact happen to be also roots of unity. But I mean, that's a fluke somehow. Yeah, and also another thing is that something very important is that here we already have a transcendental function, which is the exponential function that appears. So in fact, here we have an algebraic object, the cyclotomic unit, which is described as the value of a transcendental function. I mean, this situation is something that we'll, in fact, try to soup up more and more throughout the talk. I mean, so here's the first step, towards a generalization or more general situation, and that's the situation of elliptic units. The general idea is that the torus is supposed to be like an elliptic, sort of degenerate elliptic curve, and so constructions that you make on the torus, you should be able to replicate them on elliptic curves. And so this is what I just quickly explain here. So you can build elliptic units just as cyclotomic units are built from the torus. I mean, the elliptic units will be built from elliptic curves with potential good reduction over an algebraic number field. I'll say in a moment something about that condition. And so you take such an elliptic curve, and then you consider its complex uniformization, that is its presentation as a quotient of C by a lattice. And again, you take a point, this time of order m, just as before. You had a point of order m in the torus, and m has to be composite as well. And then we have this analytic expression here, e to the, that I'm not going to read out. The quasi-period is the quasi-period that appears in the Weierstrass P function, in the theory of elliptic functions. And sigma is the sigma function, and delta is the modular form delta. And so this is an analytic expression, and it happens that this is a unit as well. And this is called the elliptic unit. And so we are in a situation very similar to before, where we have an analytic expression, a transcendental expression for something algebraic. And this function here, which appears in the frame, is that's called a Siegel function. And in fact, if you consider tau fixed, then of course it's a function of z, so that you have a canonical function on the elliptic curve outside of 0, where there will be a pole, there will be a singularity. So, but this is a canonical function associated with E, the elliptic curve. The condition on potential good reduction, that means that if you reduce, if you write you write equations for the elliptic curve over the number field, and since you're in a projective situation, you may assume by clearing denominators that the numbers are in the ring of integers of the number field. And then, I mean, the good reduction means that you always, if you reduce them mod p, in fact, where p is some prime, the ring of integers above an actual prime number, then you should always get an elliptic curve over a finite field, but really an elliptic curve, not something degenerate. So it means that from an arithmetic point of view, you should have a smooth fibration of elliptic curves over the integers. The condition can be read on the J on the J function. If the J function is an algebraic integer, then up to an extension of the number field, it will have that property. Yeah, and so this particular situation is what I'm interested now in generalizing. And the generalization I have in mind is abelian schemes. That is, I want to consider on the one hand higher dimensional abelian varieties. That means higher dimensional, proper, and therefore commutative group schemes over in an arithmetic situation. Elliptic curves is the dimension 1 situation, and I want to consider something of higher dimensions. And also, I want to allow a larger base. You know, in this case, in fact, from an arithmetic point of view, if you really work on the ring of integers, you work over the spectrum of the ring of integers that has dimension 1. The generic fiber then is the field which has dimension 0. But you want to allow higher higher dimensions. So you want to allow fibrations in abelian varieties over a base. And in this situation, you would like to replicate this particular setup. So what is the analog of the Siegel function? And would this analog have some arithmetic significance? No, it wouldn't be a pure number field. No, it would be a scheme. I mean, that's what I'm going to do. Yeah. So now, right. So now I've explained what I have in mind, but in order to have a sort of a pointer, you know, into the direction in which one should go in order to get these objects on abelian schemes, it's important to understand why the Siegel function, of course, gives rise to a unit. I mean, that's rather basic. And here I'm going to give, in fact, I'm going to explain why that is so. I mean, outline the proof. And it's a slightly non-standard proof, although, I mean, the existing proofs can certainly be interpreted as being special, I mean, in this way. So the first thing is that I'd like to recall some results about a very classical object called the Néron-Tate height. And so, as I said, I mean, the best way, you know, is to relate them to height functions. And the Néron, you remember, the Néron-Tate height on an elliptic curve of a number field is a function on the k points, you know, of the elliptic curve, and which has the pleasant property that if you set a bound, I mean, then there will be a finite number of k points bounded with bounded height. And Tate remarked, I suppose, at the end of the 60s already, that the Néron-Tate was sort of almost quadratic. That is, that it satisfied this equality here up to a bounded function. That in fact, any height associated with the origin, I mean, that's, you have to choose. You have to make a choice before you can define a height function. Is almost quadratic in the sense that and that in fact it is possible using a simple limiting process to obtain a height which satisfies that precisely. And this is the Néron-Tate height, which has real values and can be used to, and which has this nice property that there's only a finite number of rational points with bounded height. I mean, for those of you who are more analytically minded, just to set things right, I mean, in the right context, I mean, the Néron-Tate height is in no way continuous. I mean, it's a sort of totally discontinuous object. In fact, I mean, completely arithmetic in nature. It's not at all a continuous function in any way. Now, Tate, in in fact, in an unpublished, in a letter to Serre, I think, he gave an explicit formula for the Néron-Tate height on elliptic curves. And in this situation, so you have to give a presentation of the elliptic curve, which is really in terms of equations. And it is a classical fact that an elliptic curve, I mean, which can be presented, of course, as a quotient of C by a lattice, can be presented as, by using just one projective equation, a Weierstrass equation. And in certain circumstances, even a sort of simplified form, this is the Legendre form, which I'm using now. And so in any elliptic curve can then be written in this form with some A and B. And if you have now this presentation in hand, you can then give, there's a formula for the Néron-Tate height. And so here now we work in P2. We work in P2. So here this is the affine equation, but then, so in fact you work in A2. Yeah. But although more here I'm deliberately just avoiding the point at infinity. And here now you have an affine curve. You consider a rational point on it, x, y on k squared, a point on it. And you make this assumption that it reduces into the smooth locus of the reduction of the curve. I mean, this is if the curve has good reduction, then that's automatic. Now, and here we have now this particular formula, which, and I'm going to go back to this formula a bit later, but I mean, I would just like to point out the following rather, obvious fact, which is that the Siegel function appears here again. This is the very same Siegel function. And in fact, I mean, strangely, but this is maybe due to the fact that I've overlooked something, but in the literature, this coincidence is sort of not pointed out. I've never seen it pointed out explicitly, in fact. In fact, even Lang, who has lots of books on these things, has two different books, one on units and another one on where he on Diophantine geometry, where he discusses heights, and he never points out the fact that he's actually used the same function twice. So, but anyway, so the fact that this function appears here should, of course, there must be some reason for that. I mean, indeed there is, but the thing is, you can already see from this expression, so in this expression, so what happens to this expression? Here, in fact, you consider the Siegel function, you evaluate it, but then what you do is that you consider all the possible embeddings of the number field into C, all the possible embeddings into C of the number field you're working with. And for each of these embeddings, of course, then you have a new situation, new rational point, new, etc. And for each of these situations, you evaluate the Siegel function. That means you let, in Galois terms, you let the Galois group act on the point, and you reevaluate it, on all the Galois orbits. And then, in fact, here you take the sum of the logarithms of the absolute values of for each element of the Galois orbit. This NV is 1 when it's a real embedding and 2 when it's a complex embedding. So, but I mean, the fact that you take this average here means that it's unlikely that you can really deduce, that you can really use simply the Néron-Tate height and its properties to deduce that a torsion, the Siegel function of a torsion point is a unit. Because I mean, you're always going to lose something because of this averaging process here. But on the other hand, something that shows that something in this direction should be possible to do something in this direction is simply the fact that the Néron-Tate height of a torsion point is necessarily 0. That is simply because it has this quadratic property. If you put simply m, the order of the torsion point, in it, then you have 1 minus m squared times the Néron-Tate height equals 0, hence the Néron-Tate height itself is 0. And that is and that is completely compatible with the fact that this is a unit. This is, yes, no. Why is this compatible? This is because if you write the sum, you can take the logarithm out, and then you have a product. And the product is the norm. And the norm of a unit is a unit in Z, and in Z the only units are 1 and minus 1. And therefore their absolute value is 1, and hence you get indeed that this this sum is 0. Okay, but whatever happens, we need to generalize this formula. We need something more, somewhat a little bit finer than the Néron-Tate height in order to really deduce, to get a result to get what we want. Yeah, so this is what I just said here. And now, Mazur and Tate, and that was in an article in the, in fact, they're here, I don't have the date, mid-80s, I think, but I'm not absolutely sure. They constructed a refinement, which I call here Mazur-Tate, MT, of the Néron-Tate height, and which has values in a finer group, and from which you can recover the Néron-Tate height. And in fact, I mean, with hindsight, this appears as this is already Arakilov theory sort of germinating here. So in this case, the group here that we have here, so what you do is you take a direct sum and you have the integers for each non-Archimedean valuation. That means, in fact, each prime ideal of the ring of number field. And you have the real numbers for all the Archimedean ones. And then you quotient out by the sum of the valuations of any element of the number field. In fact, this is a group which is sort of handmade in order to sort of catch what's happening in this formula. Because if you look in this formula, in fact, here there's the norm, so there's again all the Archimedean valuations that appear, here again, and here again. I mean, it is very obvious when you look at this formula that this is simply, basically, the average over something that lives in this group. I mean, this group is sort of, there's a natural morphism from that, a natural averaging function from that group into the real numbers, and the previous formula naturally sort of lands in this group first. And yeah, so here, in fact, I've written some obvious things. If you remove the Archimedean valuations from the description I've just given, in fact, you will get, if you just have to look at the definitions, but you get the definition of the class group. So if you just remove them. The fact that you add them is precisely what corresponds to this hat, and which is this very Arakilov theoretic operation, where you consider Archimedean valuations on the same footing as the non-Archimedean ones. And so there's, by construction, a natural exact sequence like this. So it surjects onto the class group. The kernel is naturally, onto the kernel there's naturally a surjection of simply the sum of all the reals you go through all the Archimedean valuations and take a sum over the real numbers each time. And then the kernel of that is, in fact, what will go into 0, which is, in fact, exactly the regulator. And the regulator is simply this. I mean, it's sum over all V Archimedean, and then you have minus log of U, like this. The regulator is just a logarithm function, in fact. Yeah, so it means you take the unit, and you look at its the norm you get for each non-Archimedean valuation, and you evaluate minus log of that. And otherwise, I mean, there is an averaging map, as I said, where you simply take the sum, which sends this class group with hat of OK onto the corresponding one for Z. And for Z, you can easily compute that it is actually simply the real numbers. fact, this can be simply seen from this sequence, because in this case, of course, the class group of the integers, on the integers, the class group is 1. And the units don't give anything, because there's just 1 and minus 1. So in fact, you end up with just R isomorphic to class group with hat of Z. And yeah, and now in the same article, Mesa and Tate show that the refined height still has this quadratic property. And they show that the same formula is valid, but simply the obvious formula, the one such that when you apply the averaging map, you get the Néron-Tate height. So that's exactly the same formula. Now, now this formula, on the other hand, and the fact that you end in a sort of finer group, that is something that really allows you to prove that torsion points give rise to units. Actually, up to a point. I mean, there's just a little something that's missing. In order to see that, I first want to sort of say some things about this formula. So in this formula, you have 3 terms. You have the a cubed b squared term, you have the denominator of the x-coordinate of the point, and then you have this transcendental part. Now, the first part, a cubed b squared, that's one, that one comes from the bad reduction of E. The fact that E might, when you reduce it mod p, give something which is not a nice smooth elliptic curve. And the second term comes from the fact that when you reduce mod p, the point might hit the origin. It might hit even when there's good reduction. I mean, the point might actually, when you reduce it mod b, suddenly coincide with 0. And this is what this measures. In fact, the denominator is precisely a measure of, how much sort of it gets close to 0 when you reduce mod p. And finally, the last term, that's the purely transcendental term. And in fact, here I'm basically giving no information other than that this is indeed well understood in Arakelov theoretic terms. Now, this means that when you look at a composite, suppose now you have an elliptic curve which has good reduction everywhere. In this case, by construction, this term is going to be 0. There won't be any such term. If suppose now you take a torsion point and you range it that this torsion point never hits 0, well, then you also don't have this. And this happens when the order of the torsion point is a composite. And the reason is that when you reduce mod p, this is injective apart from the torsion points that have an order power of p. But basically, if you choose 2 different prime numbers, that means that you force it will be the sum of 2 torsion points of different orders, and one of them is not going to hit 0. And then because of that, I mean, it very simply geometrically forces the point to never hit 0, so you don't have the contribution of this term either. So it means that when you apply mt to a torsion point, then you get only the transcendental term, only the transcendental term. On the other hand, this is also equal to 0, or at least 0 when you tensor with q. That is 0 in the group CL hat OK. It has to be 0 in the group CL hat OK for exactly the same reason as before. It's because mt is quadratic, and therefore it's killed by 1 minus m squared. So you deduce that the transcendental expression, this transcendental expression, is 0 in our group here, in this group here. But the transcendental expression, by its very nature, lives in the Archimedean part. So it means that if you say that it is 0, it means that you're actually in the image of the regulator. And being in the image of the regulator is tantamount to saying that it is minus the logarithm of a unit. So in fact, I mean, using this very simple simply looking at an exact sequence, you deduce, which in fact I should have maybe shown you at the same time as I discussed it, you obtain this result here. So if it is composite, then this here lies in the image of the Dirichlet regulator map. And consequently, this absolute value, the absolute value of the Siegel function, when evaluated as such M torsion point, is a unit. And now here is what actually I'm missing here. You see here I've taken an absolute value, whereas actually the classical theory would tell you that this is a unit without the absolute value. So this is something that I do not consider here. Here I only consider the absolute value of the unit. The imaginary part, that is actually a tricky business, and it is not clear also that Arakelov theoretic considerations are sort of the right ones to get to that. Yeah, so here so let me just sum up again what I've been doing. So there are the Siegel functions. There's a certain height function which has values in a group which is an extension of the class group, and it has sort of an axiomatic property. And then, I mean, using the fact that there's such an exact sequence, you deduce that a certain transcendental function is indeed in the image of the regulator map that is of an algebraic nature. So all this story here, the Siegel function, and this method, you know, this reasoning, I would like to replicate that on any abelian scheme. So I'm going to recall some. So in fact, the higher analog of the class group of the CL hat, I mean, that has been investigated by many people through the 80s, and a very general definition has been given by Gier and Soulet. And so here the setup is as follows. You start with a regular scheme, which is a finite type of a OK. So if you, so I mean, I won't tell you, as they did in the 60s, if you don't know what a variety is, think of a scheme, but rather if you take a scheme, it should simply be understood as, you can even think of an affine scheme, which then simply means a set of polynomials with coefficients in OK. This is how you can understand. So I mean, so geometrically speaking, it means that you have a variety which is defined by equations with values in the number field. But I mean, the scheme theoretic point of view allows you then to understand, I mean, all its reductions mod p in one fell swoop, you know, as being fibered over the integers. And so for each prime number, you have one fiber, which is the reduction mod p. And so in this case, we assume that it's regular, which, I mean, locally, this is, well, a scheme is like, is described entirely by a commutative ring, and then this commutative ring has to be regular in this case. And they define the arithmetic Chow group, which is the analog of the CL hat OK. And this is a graded group. And when you take the ring of integers of a number field, here this is usually the corresponding scheme is written as spectrum. Then in fact the first one, the first graded group, is exactly CL hat. And also, in general, in any degree, there's always an exact sequence here, which is completely analogous to the one I've written down for CL hat. So in fact, here so this is an object which is an extension of this group here without a hat, which is the ordinary Chow group. I'm going to, and the kernel is a space of differential forms. So in the case where x is a point, this will simply be copies of the real numbers. But in general, it's a space of differential forms, which I'm not going to give the definition exactly. And then here, this object is the generalization of the group of units. So this is, in this case, this is a motivic cohomology group. So this is a whole story. But there's a classical result which says that if you have the ring of integers of a number field, for instance, well then the units of this ring are actually exactly isomorphic to the group K1 of OK. And K1 is so it's a K-theory group. This was, this is a theory which was, general KNs were defined by Quillen in the early 70s, but K1 was available before. And there's a theorem which says that this particular group, this K1 group, is exactly the group of units. And in general, the motivic cohomology groups, if you tensor with Q, the problem is if you don't tensor with Q, then the story is more complicated. But if you tensor with Q, there will actually be subspaces of, there would be certain subspaces of some Kn groups of our scheme X. I'm not going to write which ones exactly, but I mean, they should be understood as, at least rationally, as subspaces of high K-theory groups of X. So these are very, objects of. And so again here, if G is equal to 1, in fact, in this case, tensoring with Q will not matter, and you will exactly get K1, and therefore the units. So in fact, behind the fact that this is a generalization of the former sequence lies also this theorem. Yeah. So this object is completely analogous to the one we had before. And the Chow group itself, let me just remind you, so the Chow group without a hat, this one, this is the cycle, this is a cycle group. So this is a very general group, which is, you can define with some regularity hypotheses on the object you consider, and it is basically, it is generated by all the cycles, that is formal linear combinations of subvarieties, mod rational equivalence, which is sort of a certain type of equivalence which generalizes equivalence of codimension 1 cycles, with the one that's known. And the arithmetic Chow group is an extension of this group, in which then rather naturally is generated by pairs, where Z is a cycle, so a linear combination of sub-schemes of X, and GZ is a green current for the cycle. And a green current is so this is a condition which is purely on the complex points, purely on the complex side. That is, you take the arithmetic object, but you only consider the complex corresponding complex solutions. And there you have this analytic condition, which tells you that delta delta bar of the cycle, multiplied with ion 2 pi, plus the Dirac current of the cycle should be smooth. So that's the green current. And then again, there's an extension of the condition on rational. But I mean, the generators are such pairs, green currents and cycles. And so, as I said, I mean, so this is an object of global Arakelov theory. And as with all things in Arakelov theory, you try to look at situations of classical algebraic geometry, typically over fields, in fact, rather than arithmetic situations to begin with. And then you try to put hats on them, see if they're analogs, you can extend them to this world. And in fact, I mean, many objects can. For instance, you also have a Chern class theory. You know, Chern classes were discussed, for instance, in Sir Michael's talk. And here they will land in this group, but you need, in this case, to consider a vector bundle together with a metric on its complex points. So that is the sort of Arakelov theoretic addition. So you mix arithmetic data, which is E, with analytic data, which is this Hermitian metric. And they have covariance and contravariance properties. So if you take a morphism which is proper, projective, and smooth over the complex points, that's the really important thing, then you can define push forwards, and in general, they're pullbacks. Now I'm preparing to formulate a theorem which, in fact, asserts the existence and the unicity of a certain current, a certain green current, on an abelian scheme. And but in order to do that, I need to do some geometry on abelian schemes. So remember, so an abelian scheme, so that fibration in abelian varieties, but in an arithmetic situation, the base being here now a regular scheme, a finite type of OK as before. So for instance, this could be okay, then you recover the situation of abelian variety. And if you then consider dimension 1, you recover the elliptic situation we considered before. And you have, for any such an object, you have the dual abelian scheme. The dual abelian scheme is it's a moduli space. Say on each fiber, it's a moduli space for the line bundles which are algebraically equivalent to 0. So pick 0. A dual, you could write pick 0 A. And as a moduli space, it naturally carries a universal, bundle and a universal deformation to 0, which is what algebraically equivalent to 0 means, which lives on the product of A and A dual. This is called the Poincaré bundle. And this Poincaré bundle, over the complex numbers, it's a flat bundle. And in fact, if you, up to a rigidification, which you choose in this situation, it has a natural Hermitian metric on the fibers. In fact, which is globally C infinity. So you end a situation where, in fact, on an abelian scheme, you have this Poincaré bundle on A cross A dual, and also it has a canonical metric, which is encouraging. Furthermore, so I need a bit of notation here. So S0, that's the zero section into A. So simply the zero section. And S0 dual is, of course, rather obviously the one for A dual. And now here comes the theorem on the existence and the unicity of a certain green current. So there is a certain real, and forget conjugation invariant, there's a certain real current, which we call GA like this, and which lives, in fact, on the dual abelian scheme. That's the natural, by dualizing everything, you can, of course, decide to always work on A. But when you have A, the construction leads you to A dual. So it's a certain real current of type G-1, G-1. Remember, G is the relative dimension of A over S, and which is a green current for the unit section of the dual abelian scheme. And furthermore, you have the following, defining sort of functional equality, which tells you that if you take the unit section and you endow it with this particular green current, well, then you will recover the following canonical object in arithmetic Chow theory. And the object is, here you've taken the Poincaré bundle, you considered its Chern character. Remember, they are Chern classes, so in particularly a Chern character. In fact, the Chern character in this case, since it's a line bundle, is simply the exponential of C1 hat of P. And you take that exponential, and then you push the whole thing down, and you take only the degree G part of that, only the G part of that. And this is a canonical element in arithmetic Chow theory in CHG. And this must be equal to precisely this, And the last property, which is very important, is the fact that this current should be invariant on the push forward by any by the multiplication by n, whatever n. In fact, if you know this for one n, you know it for all. It's sufficient to just have it for a given n, in fact. Yeah, and so I'm saying that this current, up to currents of the type delta bar, which is a indeterminacy which you cannot avoid in this setting because of the definition of the space of differential forms that appeared before, that this current is uniquely defined by these three conditions. So it's a green current of the unit section. It satisfies this, it has this connection with the Poincaré bundle, the push forward of the Poincaré bundle, and it has this distributivity property, this invariance on the multiplication by n. And so I'm not going to say much about the proof of this, but of course you will have probably already guessed that this, in particular, if you now look at what I've just said. So I've defined high analogs of the arithmetic Chow groups, and I've defined this current. Well, in fact, here, I realize now, sorry. In fact, here, you should put hats. I forgot the hats. So yeah, now go back to the situation of elliptic curves. But you have to look at the situation where you actually fibered over the integer. You have an elliptic scheme, elliptic fibration elliptic curves of a small base, like OK. And then, since by contravariant functoriality, you have a pullback map. Here, don't forget to put hats here. And then you can actually show that the Maser-Tate height that we considered before, this height of Maser-Tate, is actually given by the following formula. You can define it canonically as being simply the pullback of the direct image of the Chern character of the Poincaré bundle. And in this case, since G is equal to 1, you take the degree 1 part. This means that you'll go from CH1 to CH1, and so you'll end up in this specific class group with a hat. And so this can be shown. And furthermore, you can also show that the green current that, whose existence I've just asserted, is given by, is a Siegel function. In fact, here, sorry, I've made actually two mistakes in this. This is minus log of this. It's not the exponential. I've made two mistakes in this page, minus log. But it is the Siegel function. If you, now I would like to give an explanation, again here now, explain why, in general, you will obtain an analog of the unit construction. That is, you have this property, quadraticity property of the Maser-Tate height allowed you to show that the Siegel function has algebraic meaning. And I would just like you to show that in this setup, considering the axioms we have for the green function, the green current we are considering, that in fact, you immediately get the corresponding algebraic properties in higher dimensions. And so for this, I mean, just look at the following simple calculation. If you look at the direct image, in fact, here, to see this calculation, the best thing is to forget the hats. This has nothing to do with the hats, and it will work equally with hats. So look at this in an algebraic setting, or even homological if you want to. I mean, imagine that you land in any cohomology theory of your choice. If you take the direct image of the Chern character of the Poincaré bundle and you pull it back by n, that is by its very construction, since the base parameterizes line bundles, it's the same as putting the Poincaré bundle itself to the tensor n. That's the definition of the multiplication by n on a dual, which corresponds to the tensor product of line bundles. And here but if you do this, then you use simply the fact that the exponential function, here the Chern class will turn this, will multiply this here by n, and then you will have, and then you can take the n out, of course. And then don't forget that we take only the g part. And if you look at the contribution, that will be exactly n to the power 2g. So that means pullback of that is equal to n to the power 2g times that. And in particular, if you take a section, well then, you just if you apply the section to this equality, you get the fact that n times a section pullback is n to the power 2g times pullback of the section. And in particular, if it's a torsion section, so that it's actually killed by multiplication by n, well then you immediately get that this object here is 0 in arithmetic Chow theory. This object here is, vanishes in arithmetic Chow theory. And this is simply application of properties of the Poincaré bundle. And as a consequence, if you look at this exact sequence here, so it means that you have an object here, the green current. In fact, in this case, the green current we are outside its singularity, so it's actually a differential form. Its image in here is 0, so it is in the image of this map here from the motivic cohomology group to the differential forms. So it actually is in fact, what then one would call the Hodge realization of a certain arithmetic element, which is lies in this motivic cohomology group. So in fact, I mean, here we've replicated all the the whole story that I told you before about Siegel functions. But now one important thing that one should underline here is the fact that what in fact this whole setup shows, and what Arakelov theory shows here, is the fact that in a higher dimensional situation, that is when G is larger than 1, one should consider currents of type G minus 1, G minus 1, not functions. I'm saying this because it has been a sort of folklore question for some time, and it still is, in fact, I mean, depending on the point of view you have here, that in the same way as you can associate units to torsion points on elliptic curves, you would like to take abelian varieties and associate units to such torsion points on abelian varieties. That's what people have been interested in doing sometime. But what this here suggests is that this is not possible. What you can do, you can only do because you're in the wrong degree. What you obtain is always something which lives in this motivic cohomology group CHG G minus 1. Now, if you do this on an abelian variety, you will get the corresponding cohomology group CHG G minus 1 of OK, when G is larger than 1. But this group is 0. So in fact, this construction will not give you anything if the base is too small. In fact, the base has to have at least dimension, the dimension of the fiber. In fact, there has to be a compatibility between the base and the dimension of the fiber. And as it happens with elliptic curves, there is this compatibility. They're both 1. But for instance, this means that this here will produce something in the situation, for instance, of Hilbert modular surfaces, where you have a surface parameterizing abelian surfaces. That's the right setup. Now, where do the mathematics of Jean-Michel Bismuth play a role here? So this is what I'm going to get to now. And in fact, this is certainly the deepest aspect of this story here. I'm going to skip this because I don't have enough time. There are some further properties of these currents. So before you read this, if you are still awake, is you might, I just want to remind you that there's something for elliptic curves, also a classical thing called the second Kronecker limit formula. And in fact, the second Kronecker limit formula, you can understand it very well in terms of analytic torsion. So the analytic torsion was already defined by Kenichi Yoshikawa in his talk. And so in a non-equivalent situation was defined by Ray and Singer. And in fact, a very sort of, one way to express the second Kronecker limit formula is to say the following. It is to say that if you go back here, sorry, I'm just going to go back to the original formula. The Siegel function. Now look at the Siegel function on the elliptic curve. An elliptic curve is actually it's self-dual, isomorphic to its own dual. So it means that you might consider this point Z not simply as a point on the curve, but as a line bundle on the curve if you wish to. And in fact, if you look at the Ray-Singer torsion, the Ray-Singer analytic torsion of that line bundle, well, it is equal to this. It is equal to the Siegel function. But the fact that this is true, is not obvious. Because, I mean, the definition of the Ray-Singer torsion, it's a regularized determinants, on the zeta regularization of the eigenvalues of the Kodaira-Laplace operator, computing the cohomology of the line bundle. But the fact that this then is going to be equal to this is not obvious, and is in fact a theorem of analytic number theory called the second Kronecker limit formula. And therefore, of course, it is very tempting to again replicate this in a general high-dimensional and relative setting. So this is what I'm going to explain here in the few minutes that I've left. Yeah. So this is what I call the spectral interpretation of this current. So here, for that, we need a generalization of the Raysinger torsion to a relative situation. So Bismut and Koehler wrote an article some 15, almost 20 years ago now, where they defined a general relative analog, for any smooth proper fibration in a complex analytic setting, and with certain Koehler conditions on the fibers. You need to have a fibration of Koehler varieties with supplementary closed condition, making it into what's called the Koehler fibration. And also in fact, in general, the vector bundle has to have locally free cohomology sheaves, relative cohomology sheaves. And in this situation, they define an object, which is a differential form, which lives, in fact, precisely in this A tilde, which has already appeared in the definition of the arithmetic Chow group, and which is the high analytic torsion form. This plays a role in the arithmetic Riemann-Roch theorem. I don't have any time to discuss that. But, and so here, what we're going to consider is the following. We consider the fibration, which is simply the fibration, the trivial fibration, where you project on the second factor, of A cross A tilde. But on the other hand, I'm removing the zero section from the base. So I simply look at the A cross A tilde, project on the second factor A tilde, A wedge. That is the dual abelian scheme. A cross the dual, project to the dual, and remove zero. And then on what remains, you look at the Poincaré bundle, on the Poincaré bundle of the total space. That is important because, in fact, the Poincaré bundle, as it happens, has no cohomology at all, apart from at the 0 point. So there will be a jump. So if you want to define the torsion form, you need to be in a situation where the cohomology is locally free. For instance, 0 will do the trick. So this is what we do. So we go outside the zero section. So that's actually good because our green current will have no singularities anymore, will be a differential form. And now the result is that this green current is actually equal to the analytic torsion form of the Poincaré bundle, provided you multiply it with this tot class here.